Okay, today we're going to talk about wave interactions. So please have a couple of things out. But actually, you're only going to need your guided notes today. So please have your Chapter 8 guided notes out. There's quite a bit to fill out as we go through these slides. And that's it. So be filling them out. And what we're talking about is wave interactions. So, for example, what happens if one wave hits another wave? So there's an interaction there, and we're going to talk about what happens. Or what happens if a wave hits an obstacle or gets blocked by something? Okay, we'll talk about that. We're also going to look at what if a wave goes from one medium to another medium. So like if it's going through air, and then all of a sudden it goes through water or glass. And so we'll look at how waves behave as they interact with other things. So here we go. To start off, there's 4 wave interactions that we're going to look at. So I'd like you in your guided notes to just go ahead and write down what's in blue here. The first one is reflection. We'll talk about it in more detail later, but for right now, just write down reflection. Number 2, we're going to talk about refraction. Refraction. Okay, and then number 3 is diffraction. And number 4 is interference. So hopefully you have that written down in your notes. But let's quickly introduce them. Again, we're going to talk about them in more detail later individually. But for reflection, it's the bouncing back of a wave after striking a barrier. So this is when a wave strikes a barrier and it bounces back. Refraction is the bending of a wave as it moves from one medium to another medium. So as it goes from air to glass or air to water, the wave is going to bend a little bit, and that's called refraction. Okay, diffraction is the bending of a wave around the edge of a barrier. So this is how the wave bends as it goes around the edge of a barrier. And then finally, we'll talk about wave interference. This is the distortion of a wave when waves overlap. So when they will overlap with each other. All right, so let's start with number 1, which was reflection. Let's talk about reflection first. So here's the definition. It's the bouncing back of waves from a barrier they cannot pass through. So it's when the waves are bounced back when they hit a barrier. There's this law, it's called the law of reflection. It says that the angle of incidence equals the angle of reflection. So when we think of reflection, hopefully you're thinking about a mirror. Mirrors reflect things. A mirror will reflect light. And that's what's shown here with this diagram. We have a flashlight shining into a mirror. And according to the law of reflection, there's this angle of incidence. So I'm going to call it theta sub I. Well, the angle of incidence has got to be equal to the angle, so I'm going to call it theta r because it's the angle of reflection. So this angle right here is equal to the angle of reflection. Here's another slide that kind of shows you the law of reflection. Again, important to note that when light comes into a mirror, the angle of reflection, or the angle of incidence, is measured from this imaginary line, this line that we draw perpendicular to the surface of the mirror. So this line right here is where we measure the angle of incidence from. Well, the angle of incidence is equal to the angle of reflection. Again, it's measured from this perpendicular line to the surface, this angle right here. So for example, if this one was 50 degrees, angle of reflection is also going to be 50 degrees. All right, another slide showing the law of reflection. Always, guys, keep in mind that if you've got the mirror or the barrier that it's bouncing off of, you've got to draw this normal line, or the line perpendicular. It forms a right angle. You've got to draw that in because your angle of incidence and your angle of reflection are measured from that line. So, practice problem number 17. It says, what is the angle of reflection in the situation shown below? So I want to give you a second. Make sure that you're measuring that from the line perpendicular to the surface. So you might have to draw that in. But the angle, what I want you to find is this angle of reflection. So please take a second. If you're watching the video, please hit pause and find that angle of reflection. Once you have your answer, hit play and see if you got it right. Okay, so let's see how you did. Hopefully at this point you have an answer. But the first thing that I would do is notice this barrier. We're going to draw our line that's perpendicular to that barrier. So this line is perpendicular, which means it makes a right angle. A right angle, for example, makes 90-degree angle with the barrier. And so if this is 35, what your job will be is to figure out what's left after 90, and that angle will go right here. That will be your angle of incidence. Okay, so if you take the right angle here and calculate what's left after you subtract the 35, it should be 55-degree angle is the angle of incidence. That means our angle of reflection will also be 55 degrees. And so that's our answer. Angle of reflection is 55 degrees. Okay, let's move on and talk about the second type of wave interaction called refraction. Okay, refraction is the bending of a wave, so it's how waves bend as it passes from one medium to another medium. An example is light traveling from air to water. So it's going from air to water, it would bend because it goes from one medium to another. Or light passing through a prism. Okay, and we'll have a slide on that as well. So waves travel at different speeds through different mediums. And this is why the light waves will bend as it goes from one medium to another, is because they travel at different speeds through different mediums. This difference in speeds causes the wave to bend. Okay? So the differences in speeds through a medium causes it to bend. Here's a diagram that kind of explains what I'm trying to explain here. So if we had a light beam, so if this was a light beam coming in, and say out here was air, and let's say this was water. So the mediums are different. Well, light travels faster. So the light's going to travel faster in air than it does in water. And so because it's hitting at an angle here, I want you to pay attention to this dot and this dot. Okay, this one's going to hit the water first and it slows down. Well, this one out here is still going faster, and so it causes the light to bend. And so this is going to go faster and this one slows down, so it's going to cause it to bend at this angle through the water. Now once it's all in the water, it goes at the same angle through the water, but then notice as it exits, okay, this one is going to exit first because it was at a slight angle here. It's going to exit first and start going faster. Well, this one's going to go slower because it's still in the water, and so again that angle is bent. So as it goes from one medium to another medium, you see the light waves are going to bend. And so that's what causes refraction, is it goes at different speeds through different mediums. And here's an example of that. If this is air out here, and this is glass, okay? the glass is going to cause that light that's coming in to bend a little bit. But when it exits, it's going to come back out at the same angle it came in at. If we look at this one over here, we got water. So if I asked you, what bends the light more, would it be when it goes from air to glass or air to water? And so it looks like to me that the glass is actually bending the light coming into it more than the water does. And so it just kind of emphasizes the point that how much it bends the light is dependent upon the medium that it's going into. One application of this would be if you were to look at a fish underwater. If you were to look at it, it would look like the fish is right here. That's the apparent location of the fish. But the actual location of that fish would be a little bit lower, or in front and below. And so if you were a spear fisherman and you wanted to spear this fish, it would look like you would have to throw it here, but you better aim a little bit lower than where the apparent image of that fish is. Here's a great example of refraction. If you put a pencil in a glass of water, and if you look at it from different angles, you can start to see where the pencil looks like it's broke. But if you pull the pencil out of the water, of course it's not broken. What's causing this optical illusion is refraction. So when light goes into the water, it bends the light, and that's what's causing it to look like the pencil is broken there. Another application of refraction is a prism. So what a prism does is it takes white light. So if you shine a light into a prism, white light is made up of all of the colors of Roy G. Biv. So white light includes all of Roy G. Biv. But what a prism will do is it separates the light into the different colors. And so it projects a rainbow if you shine white light through a prism. It's the same thing that happens when you see a rainbow. Except for when you see a rainbow, it's not a prism that's separating the light, but a water droplet. And so if the sun shines through a water droplet, those light rays are going to be bent, and you'll see different colors here. And that's what projects a rainbow into the sky. All right, let's move on to the third type of wave interaction. This is called diffraction. Diffraction is the bending of a wave around the edge of a barrier. So again, the waves are bending, but what's causing it to bend in diffraction is a barrier. And one illustration of this is when you talk to somebody in your house that's in a different room, they can still hear you if you speak loud enough, because those sound waves are being bent around the barrier. And so there's the bending of a wave around the edge of a barrier. Light waves also are able to be diffracted. Maybe not as much as sound waves, but light waves also bend around a barrier. And here's a slide that kind of illustrates that. So if we have some waves coming in, the blue lines are these waves, and this red rectangle here is a barrier. You might expect that the waves would just be reflected off of this barrier, and they are, but you might expect that there would be nothing down here because there's a barrier blocking it. But what you actually see is in diffraction is that there's this bending of the wave as it goes around the barrier. So even though there's this barrier here, sound and light can still bend around it. Another illustration of this is if we had a barrier in a small opening, sound or light even coming through this small opening will still be bent around and able to go around the barrier like that. Here's an example in a lot of places around the coastline where they have a harbor or a lot of boats in there. What they do is they build a large barrier here. So this darker shaped object is a barrier. And what they're trying to do is calm the waves as the waves come in here from the ocean. If the seas are pretty rough, the waves can come in and cause a lot of damage to boats that are just sitting in the harbor. So they build these barriers to try and block the waves. Well, because of diffraction, these waves, and you'll see them, actually can bend around. I guess it would come in like this, and they're still bending around that barrier. So now, of course, it does help because these diffracted waves are not as tall, or they don't have the amplitude that the waves out here in the ocean would have. So it does help, but there is still some waves that are able to get around it. And that's because of diffraction. Okay, the final wave interaction that we'd like to talk about today is wave interference. So interference occurs when two waves overlap each other. So when two waves overlap each other. There's two types of wave interference. Wave interference can either be what is called constructive or destructive. So when I think of these words, constructive reminds me of construction, so to build. So if you would make a note in your notes, constructive means to build, and destructive means to destroy the wave. So in constructive interference, we're building the wave. In destructive interference, we're destroying the wave. Okay, so let's go into constructive interference first. Constructive interference occurs when waves overlap so that the crest of one wave are over the crest of another wave. Also, the troughs line up. So the trough of one wave is over the trough of another wave. And this results in two waves' amplitudes. So the waves' amplitudes are added together, or constructed, or builded, or built together. Sorry, they're built together. And so the wave's amplitude is even larger than a single wave would have. Okay, and I'll show you a picture of that on the next slide. Let's introduce and contrast that to destructive interference. This occurs when the waves overlap so that the crest of one wave is over the top of a trough of the other one. So the crest is over the top of a trough of another wave, or the trough of one wave is over the crest of another wave. Okay, when destructive interference occurs, this results in the two waves' amplitudes being subtracted. So the amplitude is now being destroyed, or smaller. Okay, this slide will helpfully illustrate constructive and destructive interference. So let's look at constructive interference first. Let's go to this key right here and look at it. Wave 1 is a solid black line. Wave 2 is a dotted line. This larger blocked line, this dashed line, is when you add wave 1 and wave 2 together. When you add them together, that's what you will get. And so let's look at constructive interference. Wave 1 is this black line, and you see it's at a crest here. Well, so is wave 2, this small dotted line. It's at a crest. And so constructive interference occurs when you have a crest of one wave over the top of a crest of another wave. What happens with constructive interference is now, if you added these two waves together, you have to add their amplitudes together. And so the resulting wave is going to be a wave with a much larger amplitude. But also the trough, so wave 1's trough is here and wave 2's trough is here, you add the amplitude of the troughs together. And so this resulting wave is a lot larger in terms of its amplitude than either of the original waves. So the amplitude is increased. And so when I think of constructive, I think of construction and building the amplitude, so the wave gets larger. Now let's look at destructive interference and try to understand what's happening here. Wave 1 has a trough at this point. Trough. And wave 2 has a crest. And so what happens when you add them together is that this resulting wave is going to have an amplitude that is much smaller of either of these two waves originally. So the amplitude is being destroyed or made smaller. The amplitude is decreased. One application of this, maybe you've experienced this, if you've ever gone boating, okay, and you've gone boating and you've rowed on a tube. So what the boat driver will do a lot of times is the boat driver just sits there and drives in circles. Okay, the boat driver just goes in circles and then you're being pulled in the tube. Why does the boat driver drive in circles like that? And the answer, hopefully you're thinking to yourself, that the wake or the waves that's produced by the boat, what the boat driver is trying to do is cause constructive interference with these waves all meeting in the center here, where the waves could be larger amplitude or a larger wave would result. And so then what they'll do is they'll kind of come out and then whip you through the middle there where the waves are really tall. And anyway, maybe you've experienced that, but there's one application of wave interference. I've got a couple of practice problems that I would like to go through now dealing with wave interference. Practice problem number 18, let's do it. It says several positions along the medium are labeled with a letter. So you'll notice down here all the letters, starting with G going to all the way to O. It says to categorize each labeled position along the medium as being a position where either constructive or destructive interference would occur. So before I let you go and try this one, this dark line right here, this would be the origin or the rest position of these waves. So I'm going to do G with you right now. So at point G, which is right here, would we see constructive or destructive interference? And hopefully you're thinking to yourself it's constructive, because we have the crest of one wave, and this is a crest, at least it's above the origin. And so they're both above the origin, it's going to be constructive interference. So for point G, I would say it's constructive interference is going to occur right there. Now what I would like you to do is take a second. If you're watching the video, please hit pause and go ahead and label either constructive or destructive interference for H through O. So please go ahead and try that now. If you're watching the video, please hit pause until you do have an answer and then hit play. Okay, hopefully at this point you have an answer, but let's look and see how you did. At point H, we see a trough of one wave and the crest of another wave. So because one is a crest and one is a trough, the resulting wave is going to be smaller, so that's a destructive interference at H. I, let's look at point I now. We have a trough and a crest. Again, at point I, it's going to be destructive interference. At point J, now we have two troughs. So if they're both on the same side, it's going to be constructive interference. So at J, I would say is constructive. At point K, we have a trough and a crest. So they're on opposite sides. The resulting wave would be destructive interference or have a smaller amplitude. At point L, we have a trough and a crest. So again, it's destructive. M, we have a trough and a trough. So M is going to be constructive. At point N, we have a crest and a crest. So that's going to be constructive. And point O, we have a trough and a crest. So if they're on opposite sides, it's going to be destroyed, or the amplitude will be smaller. So that's destructive interference. Okay, so hopefully you got that right. Let me show you the answers in a little better format here. So hopefully you got this on your guided notes. The constructive interference was at G, J, M, and N. and destructive was at H, I, K, L, and O. All right, I've got another practice problem to try with wave interference. I've got the picture on the next slide, but let me explain what you're supposed to do with the picture so that when we go to the next slide, you'll know how to do it. It says 2 water bugs are both creating a series of circular waves by moving their legs in the water. So they're just insects in the water and they're causing waves by moving their legs. The waves undergo interference and create a pattern represented in the diagram on the next slide. Now, important to remember, the thick lines in the diagram on the next slide represent crest. So if they're thick lines, it's going to be a crest. And the thin lines represent wave troughs. Several of the positions in the water are labeled with a letter. Categorize each labeled position as either being a place where there is constructive interference or destructive interference. Okay, so let me show you that picture and help you through the first part of it here. So here's our 2 insects in the water. What they're doing is moving their legs and causing these wave patterns. Remember, a thick line is a crest and the thin line is a trough. So at point A, would you see constructive or destructive interference here? Well, it looks like there's a thick line and another thick line. So this is 2 crests are going to meet at point A. So this is going to be constructive interference. What I would like you to do now is go through, for these other locations, B, C, D, E, and F, and tell me whether it's constructive or destructive interference at those points. If you're watching the video, please hit pause at this point. Once you have an answer, then go ahead and hit play. Okay, let's see how you guys did with that. At point B, it looks like a thick line, so that's a crest, and another thick line is a crest. So when 2 crests meet, that is constructive interference. Let's go to location C here. There was a thick line, so that's a crest, and a thin line, that's a trough. And so at this point C, we would see destructive interference, and the wave would be smaller in terms of its amplitude. There might not even be a wave at all at point C. Now let's go to point D. Again, we have a thick line and a thin line. So that was going to be destructive interference. That's a D. At point E, it looks like we have a thick line and a thin line. So that's again destructive interference. And F, we have a thick line, which is a crest, and a thin line, which is a trough. So that is going to be destructive interference. So where would you see the largest waves? You're going to see the largest waves where there's constructive interference. So at this point, there's going to be a larger wave. At point B, it's going to be larger. And at all these other points, the wave is going to be at it will be smaller at these locations. Then there might not even be a wave at all if it totally cancels each other out. Okay, so here's the answers in a little better format. The constructive interference was at A and B. The destructive interference was at all the other points. Okay, I've got one more thing to talk about in this lesson. They're called standing waves. A standing wave is a type of wave interference where a wave reflects off a barrier and interferes with incoming waves. So let me say that again. It's where a wave reflects off of a barrier and interferes with incoming waves. We see this. We saw this in class with the slinkies. If you have your partner just hold the slinky at a rest position and you are moving it up and down, you'll see that the waves are reflected off of the barrier, off of your partner's end, and come back to you. And this is a type of wave interference we call a standing wave. In a standing wave, there's a couple of locations that I want you to know and be aware of. One is called an antinode. At the antinode, this is where there's maximum displacement of the wave. So the wave is seeing a large displacement in terms of its position from the rest or the origin position. Another location is called the node. Nodes are places where you see minimum displacement from its rest position. So antinodes are where you see maximum displacement, and nodes are where you see minimum displacement. Let me show you a picture, and this will make more sense. If this was you and you're moving the slinky up and down, and this was your partner over here, and he's just holding it level, just holding it in place. When you start moving it up and down, you're sending a wave to your partner. Well, that wave gets reflected, and so it starts sending a wave back. And if you get it the right movement here, you can set up what is known as a standing wave. In a standing wave, we see two things happening. We see areas where there's large displacement. And so this right here would be called an antinode. And we also see areas where there is minimum displacement, which we call nodes. And so I'm going to put a dot every place there's a node. So there's a node here where you're starting. There would be a node here, here, and here. The antinodes would be 1, 2, and 3. Okay, let's see if you've got this. I've got a practice problem. Practice problem number 20. It says draw a standing wave with 6 nodes and 5 antinodes. Let me help you get started. There's going to be a node here at the beginning, and there's going to be a node where it's reflecting off of it. So there's 2 of the 6 nodes. So your job will be to put 4 more nodes in here, draw the wave, the standing wave, and show me where the 5 antinodes are at. So try it. If you're watching the video, please hit pause right now and try it. At least give it a shot to see if you can get it right. Once you have an answer, hit play. Okay, so hopefully at this point you have tried to draw your standing wave with 6 nodes and 5 antinodes. So I've already got 2 nodes in here, 1 and 2. So I need 4 more. I'm just going to try to put them equal distance apart. So 1, 2, 3, and 4. Okay, now if I send a wave like with a slinky, so I'm going to send this wave. Okay, and I'm going to send it down to my partner who's holding it still, right there. What's going to happen is it's going to reflect, so it's going to come off at the opposite angle, but it's going to meet together at these places called nodes. And so that's what the standing wave should look like. We've got 1, 2, 3, 4, 5, 6 nodes, so I've got those. And we should have 5 antinodes. 1, 2, 3, 4, and 5. Okay, that's a standing wave. It's a type of wave interference. What I would like to finish with is this slide. Okay, let's summarize everything that we just learned about. So we're talking about wave interactions today. We went through 4 main types of wave interactions: reflection, refraction, diffraction, and wave interference. What I would like you to do is match each of these with the correct letter down here next to what's happening. So, for example, reflection. Find the picture down there that represents reflection and put that next to the reflection part, or at least think about it. Okay, so let me give you some time. Try to see where A, B, C, and D go, what type of wave interaction they are, and see if you can't get it right. So please hit pause on your video at this point and try to get those right. Once you have your answers, then hit play and see if you did get them right. Okay, so hopefully you were able to do that and match these up. Let's go through this and see if you got them right. Reflection is where a wave bounces off of a barrier. So where do we see a wave bouncing off of a barrier? Okay, and this is a perfect example of reflection down here. This is your mirror on your car is reflecting the light that's coming in. And so that's reflection. So I would put C for number 1. Number 2, let's go to refraction. This is where light is bent, or any waves are bent when they go from one medium to another medium. And where do we see that happening? We see that happening at B here. When the sunlight goes through air and then all of a sudden it has to go through water, it's bent. And so it's bent, and sunlight contains white light, and so it bends it, and it comes out as Roy G. Biv, and that's what a rainbow is. And so that's exactly what happens when you see a rainbow in the sky. So I would say refraction here would be B. Okay, now let's go to diffraction. If you remember, diffraction is when a wave is bent around the edge of a barrier. And the letter that illustrates diffraction is D. For example, if he's got a radio, these sound waves are being bent around the corner of this wall, and he can still hear the music being played even though he's around the corner. And so these sound waves are being bent around a barrier. So for diffraction, I would say would be D. Okay? Now obviously interference is going to be A, but let's talk about it. Okay? These two guys are fishing. If they cast at the same time, and their bait hits the water at the same time, or maybe their bobber, it's going to cause these waves in the water. And you'll see areas in between where maybe the crest overlap with another crest, and you'll see constructive interference. Or maybe the crest overlaps with the trough, and you'll see destructive interference. Anyway, that's a perfect example of wave interference. All right, hopefully that helps, guys, with all these wave interactions. Again, there's reflection, refraction, diffraction, and interference. Please review those if you need to. They will be tested, okay? So hopefully that makes sense and you understand a little bit more about wave interactions. And hopefully this video helped.